I think online task work is the future. You might be surprised to learn that 1 in 20 US adults made money from online tasks as of 2016. And this is more than twice as much as made money on ride-hailing services like Uber and Lyft. Just they're a little less visible. And so this isn't casual work. For nearly 60% of these people, they cited this work as being essential or important for meeting their basic needs. And also, it's projected to grow. So by 2027, more than half of US workers are expected to freelance. And this is being driven by largely a huge need from employers to do things like enable services. Workers filter inappropriate photos on Facebook in real time. Also training machine learning algorithms. The new deep learning algorithms require huge amounts of labeled data, and this is typically labeled using online task work, as well as making scientific discoveries. People will volunteer their time to do things like label galaxies, and this is really beneficial. So employers face two primary challenges to creating this kind of work. The first challenge has to do with task creation. So suppose you want someone to label a bunch of images. Well, it's really difficult to try to tell someone how to label these for you, and you might not even know exactly what to do in all the cases. And then the second challenge is, how do we manage a lot of distributed people working on a task and make this efficient? And if this process doesn't work well, then you might as well just hire an expert or a set of experts that require less management. And so these costs need to be paid not just once, but many times. Like for every new machine learning task that you create, one has to invest in these costs. So but is creating and managing tasks really that difficult? So suppose you've heard crowdsourcing success stories and you want to hire workers to label images of cars like this. Your first version of the instructions that you would give to workers might just say, is this a car? But maybe you look through your data before launching and you find this example of a car. So how many people think this is a car? Show of hands, maybe? Okay, maybe half-half. All right, I better go and update the instructions to specify it has to be a real car, right? Not a cartoon car. And now maybe you've launched the task and you've noticed that workers disagree on this item. And so you better update the instructions again. And so on. And almost every task has a long tail of special cases that one needs to handle in order to get good quality work. Am I in the way or am I good? OK. Yeah, so here's an interior of a car, right? So a day in the life of a requester or an employer or task designer typically starts with creating a set of instructions, performing a sample of tasks yourself, maybe revising these instructions, launching the task, revising instructions again. And then now maybe your instructions are quite complicated, so you might need to create a teaching and testing procedure to make sure that workers understand them. And then maybe also you need to write management algorithms to try to reduce the cost of this process so that it's actually worthwhile to crowdsource and not just hire a group of experts. And so this is the dirty secret of crowdsourcing, that everyone makes it seem really, really easy and a good solution, but unless you do all this work, it doesn't work very well. So what if an artificial agent did most of this work for you? This would help requesters a lot in terms of reducing the cost of task creation and management, as well as reducing the overall cost of work. And workers would be more satisfied because the task would be more clear. It would be more affordable, so more employers would use crowdsourcing. And for workers, it would also produce more work and better work. And this is important given that increasing numbers of people are participating in online work. But there are some particular challenges with designing an artificial agent to interact with people. So first, there's typically ill-defined rewards. Like it was difficult to specify what to do. There's typically also small data, so we can't train on huge amounts of data. With our agent, it has to learn how to act on a new problem in a new environment. And it needs to act with real people, and this is expensive. There's no simulator because people are difficult to simulate. And also, agent learning must be efficient and safe. So people's lives are depending on this. You don't want to fire people for no reason, for example. And there's also some special challenges like combinatorial coordination problems, like how do you choose the right set of questions or the right ordering of questions, which don't necessarily fit in the standard supervised reinforcement learning framework. So to give you I build agents that can overcome these challenges. And I've worked on a bunch of problems in this space, from how do we prioritize work to be more efficient, to how do we route work to the right workers so that also to improve efficiency and cost. How do we adaptively test workers and train them in an efficient way. And overall, I would categorize this part of my work as task sequencing. And we wrote a book chapter about how we can use AI to improve basically sequencing of crowdsourcing tasks and improve outcomes this way. But we're also designing agents to interact with people, so there's also human-computer interaction problems that are important. And so I've worked on how do we align agent values with what we actually want people to do. Can we create workflows and interactions between people that will improve the quality over just asking people to do independent work? And also looked at some ethical treatment of workers, like how do we, how can workers subcontract work to other workers, and can they own parts of the models that they're training? And currently I'm focused on how can we go beyond task sequencing and support workers inside of the tasks and do this for more complex tasks. So in this talk, I want to talk about 3 projects here that highlight how we can overcome some of these challenges that I motivated just a bit ago. And then talk a little bit about future work in this space. Oh, there's a delay. In this space of in-task or complex work. So the 3 problems that I'm going to talk about are prioritizing work, and how can we overcome the problem of choosing from a combinatorial number of orderings or sets of questions. How can we take this prioritized work and make sure that workers are tested and are doing well on it? And how can we do this in a small data regime where we have to learn safely and efficiently? And finally, how can we tackle this ill-defined rewards problem and align the agent behavior with what we actually want to do through task design? So let's dive into the first problem. So if you recall this labeling task with an image and you want to decide if it's a car or not, another version of this is you might want to ask multiple questions, not just one question. You might want to ask, is there a car, is there a vehicle, is there a person, et cetera. And so this is a standard machine learning problem called multi-label classification, where instead of trying to map each item to a single answer, we want to map it to a set of labels that applies. And so if you wanted to design an agent to support this, the agent might be given a budget, and then the task for the agent is to predict the labels that apply to each item. And the agent can take actions by issuing tasks to workers to choose which labels apply to the item. So your entities here might be people and places, for example, and your labels might be categories of these people and places. And one standard solution here might be to take each item and label, and then solve this as a standard classification problem. So you might ask some number of workers whether or not the label applies to the item, and some workers might say true, might say false. And then we'll accept that the label applies if there's a majority, for example, that say true. And so there's been some work on optimizing these kinds of classification questions through models that predict what the right answer is and learning control policies. But our observation for this problem is that labels aren't independent, right? So your initial belief, the agent's initial belief about whether or not each of these labels apply might be 0.5, it doesn't know anything. And then it has a decision to make about which label to ask. So it could ask about vehicle or person. And if it asks about vehicle and a worker says yes, then it might increase its probability that vehicle applies, but also alter the other probabilities, right? So if it's a vehicle, it's also more likely to be a car, and so on. And you might not have an initial graph that tells you, like you might be able to, if you had a taxonomy, you might be able to infer this from the taxonomy, but we don't assume that. But there's still these latent relationships between labels. The other option of choosing between person might also alter the probabilities somehow. But maybe vehicle is a better question to ask because it results in a lower entropy state. So assuming that the model of the agent is correct, the goal of the agent should be to try to minimize the entropy of the distribution or be fully confident that each label either applies or doesn't apply. And in order to update the agent's beliefs, we need to come up with some sort of model. And so what we did here is we created a simple model with a two-level tree where here's the tree for predicting whether car applies. And the children are all the other labels. And then here, the children of each label are the votes that workers have answered about the label. So here's a diagram showing that 2 workers have answered true, that a vehicle applies, and one worker has answered false. And then we can use inference to predict how likely a car is given this information. So we also model workers using a simple 2-parameter worker skill model where that the correctness of the worker depends on whether or not the label is true or not. And then given this model, we can formulate an optimization problem of how do we optimize the information gain, or this is the difference in entropy. So we want to try to get to the lowest entropy state and choose the label to ask a vote about that will result in the largest decrease in entropy. And so if you remember in our model, looks like this, that you can kind of see that the worker votes are independent given the labels. Because if you know the values of each label, then learning about observing one worker vote doesn't give you information about the other ones. So this gives us some nice properties. The first property is that we can simplify this entropy calculation to be just local entropies and not reason about the entire distribution of labels. And then the second nice benefit is that we can prove that information gain is submodular in this case, which means that submodularity is basically a diminishing returns property. Like if you ask about a vote in the future, it's not going to provide you any more information than if you ask about it now. Kind of like information doesn't hurt. And given this property, we don't need to do any fancy search. We can just select votes greedily using a myopic policy, and we get some nice guarantees on how well this will do. So we conducted an experiment to see how well this works in practice using these entities and some labels from prior work. And we collected answers from many workers for each item label combination. And we overcollected these so that we could then simulate how well different policies do after the fact and like replay the worker votes. This just makes the experiment less expensive to run. So the results are here. The x-axis is the total number of questions that the agent has asked for one item. And the y-axis is a measure of performance on how accurate the label predictions are. And here, the majority vote point from prior work is that we've asked about 33 of the labels 5 times each. So it's 165 over there. And instead, if we use this submodular, if we use a greedy strategy but use an independent model that doesn't capture the dependence between labels, we can get a curve that does much better than just asking 5 times about every label. But if we also model the label dependence using this 2-level tree, then we can do much better still. So in particular, this means that we can get the same accuracy or the same F-score as majority vote using less than 10% of the labor. So I think it's really this is a really cool result, and everyone should be using this for your multi-label classification problems.
So can I just ask a little bit more about that?
Yeah.
I know you have a lot of other interesting things to get to, but this is a very cool result. I'm just wondering, empirically, what does this scale with? Because 10% is great. On the other hand, if you think in total dollar amount, in this example, you know, if I'm willing to spend an additional, 25 big ones,
right.
It washes out because they asked them to. But does that number change with the number of entities, or what makes this? How do I use this to save $1 million? Is a pointed way to put the question.
Yeah, I mean, so this is the cost for one item. So so if your budget is really large, right, then you would normally spend $2 million or something, then this would be a large savings, right? I mean, I think in terms of scaling with the number of labels, it also like if you have one label you were asking about, it's not going to provide much benefit, right? But so I think it also scales with that. But
so you need a large number of items and at least 3, 5 labels per.
Yeah, I think so. We didn't look at really reducing the number of labels too much, but
Okay.
I think so.
Thanks.
Yeah.
But the system is learning the probabilistic, the relationships between the labels as it goes, right? So
Yeah.
If there's a very large number of labels, then
It'll take longer.
there's going to be even more benefit as well,
Right.
Depending on what the relationships really are.
Yeah, I mean, it might take longer also to learn a good model. But so here, this was trained on 99 items, and then this is like the cost for the savings for the 100th item. But yeah, I think the more dependence between the labels, the more benefit, for example. Although the independent model does fairly well as well. So yeah, so this was the first work on this multi-label classification problem for crowdsourcing, and people have used similar techniques for optimizing other kinds of workflows. So now I'd like to move on from how can we prioritize. So I guess to summarize this part, we achieved an efficiency improvement of 10x. We also were able to prove some theoretical guarantees on how can we select labels of sets of labels. And we did this using submodular optimization. And now I'd like to switch gears to if we're prioritizing this work, we want to make sure that the workers that are doing the work are performing well and are tested, and how can we do this efficiently given that we have a small data regime and we can't observe many workers up front necessarily. So a common approach to quality control and crowdsourcing is to insert gold test questions that you know the answers to a stream of questions that the worker is answering. And but it's difficult to determine the optimal ratio of this. So if you always test a worker on every question, you're not going to get any work done that you actually care about. If you never test the worker, then workers that don't perform well might get through and lower your data quality. So, but it's difficult to determine the right ratio. So people tend to do ad hoc things. We surveyed what some other researchers had done, and they chose very wide-ranging fractions of test questions as well as accuracy thresholds for cutting off. And so we thought this was a perfect opportunity, instead of setting this in an ad hoc way, to learn this from data in a more principled way. So suppose you're a crowdsourcing requester and you want answers above some accuracy A star. You might also have some base policy that you can provide to the agent. Like if the agent weren't there, I would test 20% of the time. So that's what the base policy is. And then the agent's going to learn a better model, use this base policy, and then learn a better model. So the actions that the agent can take in the environment are to ask a worker a test question, ask them a work question, or replace the worker with another worker. And the observations that the agent can make are whether the test answer is correct or incorrect, because it knows the ground truth for the test, and also if the worker leaves. And the reward function is set so that only workers above this accuracy A star will, in expectation, give positive reward, and workers below the A star will give negative reward. But the key thing to notice here is that this reward signal is unobservable, so it's not a standard reinforcement learning problem because we can't observe the correctness of the work answers. So the way that we accomplish this is, so these are the two challenges, that they're unobservable rewards, and also that we want our exploration to be safe. Like we don't want to unfairly reject workers when we shouldn't be. And so our approach is to explore with this requester base policy, and then to fit a partially observable Markov decision process that will help us estimate what the worker accuracy is, and then use that to plan and figure out how much to test them. And then once we've learned that model, then we can exploit with that model. And so this can be seen as kind of epsilon first exploration with a human base policy. And to go into a little more details of how we formulate the partially observable Markov decision process, there's a hidden state of the worker, and then there's also a terminal state. And so the agent can take actions like test a worker, in which case they could transition to another hidden state or stay at the same state, or they could leave the system. And for testing, the agent doesn't get any reward, but it can observe whether or not it's correct, the answer is correct or incorrect, which means it can gather information about the worker. The agent can also ask a work question it doesn't know the answer to, and in this case, it'll get some reward that's a positive reward if the worker is in general above the accuracy that we want, and a negative reward in expectation if the worker is below. And the agent can also replace the worker with a new one, as I mentioned. So these are the basic actions that the agent can take. And then to expand on what the hidden state of the workers that we assumed are, we assumed that workers could either be above or below our accuracy threshold. Like they could either, and we call this skillful or not skillful. And that agents could also be, workers could also be diligent or not diligent. So perhaps they start diligent and then at some point they might get tired and they might start providing lower quality answers. And this is the whole reason why people tend to continue to test workers. This may or may not be true, but this is why continued testing happens. And so our model has a small number of parameters that we need to estimate, just these accuracies, as well as a few additional parameters like what's the fraction of skillful to non-skillful workers in the environment, and things like that. But it's a small number, so this helps us learn given a small amount of data. So we conducted some experiments to see how well this worked. We took existing data sets and set the desired accuracy to be something that was achievable from observing the data. And the task that these data sets came from is a named entity linking task, which you're probably all familiar with. But given a text and a mention of an entity like Washington, the task is to disambiguate which Washington this refers to. And then we can simulate policies like we did in the previous work by basically just terminating workers early if we want to replace the worker with a different one. And so the policies we tested are a work-only policy where we don't test at all, a test and replace policy where we test with this recommended 20%. This is what a major platform recommended 20%. So we use that. And then our POMDP algorithm will use this base policy and explore with it for 20 workers, and then switch over to the learned policy. So to look at the results here, again, the x-axis is the number of questions that the agent has asked. The y-axis is this cumulative reward. And if we just do work all the time and don't ask any test questions, this is the blue line. So we tend to get negative reward because workers on average are not above the A star. If we test 20% of the time, that's the green line. It gets a positive reward. But the red curve is our approach, which follows the green line during the exploration phase, but then is able to learn a better policy than the base policy. And so again, if we want to look at how much better this is doing in terms of our reward function, it's like doubling the amount of reward. So again, it's kind of a no-brainer here because you're following some base policy and then just doing better than it. And so we had some extensions also that supported not just testing workers, but can we train them to do better? Do you have a question?
Yeah. Ask a question. So I get that you get reward over time. The part that I was a little confused about is how you came up with the 85% precision, because I think interoperator agreement is super dependent on the task.
Yeah.
And so I'm wondering, like, how does the 85% fit into this? And then the cost of rejecting workers over, is that factored into the reward? If you're rejecting people who don't meet the 85% threshold, some of those will be false negatives, right? And is that, I'm not understanding how that's factored into the result there.
Yeah, so there's no explicit penalty for firing someone that we shouldn't have fired, like in our reward function. It's just probably not a great outcome. But in terms of the 85%, we just for the experiment purposes, we looked at the data and then we chose a value that was achievable. So you might imagine the requester might want like 100% accuracy, and that might not be achievable. In which case, like all the curves will be negative. But I guess it's still in that case we would hope that our agent would learn. So in that case, our agent might learn a policy that's like always firing workers because no worker is up to that up to that reward. So the best thing to do is just like not hire anyone. So the behavior should depend on this accuracy that you choose, as well as like the learned fraction of workers that you see in the environment.
Okay, just to clarify, so we don't know like what percent of workers made it to like question 3,000. Could be 10%, and we're replacing them or not.
Yeah, this plot doesn't, like, it's not captured in the reward function.
Got it.
Yeah.
Do you have a sense of how much more time is being taken to complete the same number of annotations under a policy that presumably would reject more people?
So the reward function doesn't capture, it has 0 reward for testing.
Right.
And so like any point in the x-axis is the same amount of annotations that you've gotten.
Yeah, I guess I'm just asking, like, empirically, when you observe, like, there's a cost associated to getting increased reward.
Right.
Which is time,
Yeah.
probably.
Yeah, it's
So
like,
I was kind of curious what you found.
yeah, well, I mean, the x-axis is the time, like the number of questions that we've asked. So if you just ask test questions all the time, you're not going to get any reward at all. But if you ask, so it learns some ratio. I don't know what the exact ratios are, but if that's what you're asking. Yeah. So I think in general, these kind of approaches, there's been some related work on, like in education, how do you sequence levels and do that sort of thing, but no one had looked at how do we adaptively test workers, and that's what this work was about. So to summarize here, we were able to outperform like a fixed recommended policy by more than 100% to handle unobservable rewards using a POMDP-based approach. And the agent was able to explore safely using this base policy that was specified by the requester. And so for the last part of the last project I want to talk about, I want to switch gears from talking about task sequencing to talking about a more human problem of how can we design tools to help support task design. And this overcomes the AI challenge of that rewards tend to be ill-defined in the real world, and so we built a tool to help with this. So if you recall our original motivating example of a set of images and trying to create instructions for labeling, why was this difficult? It was difficult because we had this iterative task design loop where the requester needed to perform the task and explore the task. And as you're exploring the task, you might get a better sense of what your concept is, and your concept might also change. So previous researchers have called this concept evolution. But you also need to run the task, to debug the task, because you might not initially know what workers would be confused about. And to learn like what the model mismatches between the workers and yourself, you need to run it and see what confuses them. And for after you perform each of these steps, you need to revise the instructions, and you also may need to revise the training and testing procedure to make sure that workers are doing a good job. And this is actually a big deal. Requesters cite this as one of their major problems they face and a major time sink for them. And they're also frustrated with quality control, largely because they often blame the workers, but in many cases, like the task is unclear. And so the problems that workers face, there was a recent survey of Amazon Mechanical Turk workers, and the top 3 concerns that they cited were flaws in the task or interface design, unclear evaluation criteria, and unresponsive or arbitrary resolution of rejections. So I think clearly these issues have a lot to do with task design. And so we wanted to build a tool to make this process easier and better, so we built a way to use the crowd to debug your task. So the way that our system called Sprout works is it launches a bunch of tasks to use the crowd to debug the task. The crowd creates these confusions that the requester can explore in a prioritized way. So for instance, the largest confusion might be, the confusion with the most amount of items might be multiple cars and so on. And here each square denotes an item. So the requester can look through these clusters and then edit their instructions to address these confusions. And then the tool can rerun this new version of the instructions, which can update the confusions and you can continue this process until the instructions are, the task is defined the way that you want. So Sprout also provides some additional support in terms of visualizing the amount of disagreement and the average answer that workers were providing, as well as helping you keep track of your progress on the overall task. And it also lets the requester create test questions that are good for testing the instructions, as well as embedding examples in the instructions to help the workers understand what the text actually means. And so it might be difficult to find the right test questions that correspond to the instructions, so the system can suggest test questions that are related to these examples and help to speed up that process as well. And this is indicate that the requester can drag them to the appropriate box. So after the requester creates the instructions, our tool compiles these into a training and testing workflow, which is called gated instruction. And so we had a NACL paper on this on how we can, this is a simple workflow for improving quality by first creating an interactive tutorial for workers where workers get feedback on the questions they're answering, and then a test phase where they have to answer related questions but they don't get feedback. And then if they don't pass the test, then they're removed from the task, and if they do, they're allowed to continue. So this is a simple but effective way of creating instructions that's more interactive than just a single page. And so this is what we compile it into. And our overall interface looks like this. It's got a lot going on, but it's basically the React version of the cartoon that I showed you earlier. So far I've only talked about the requester interface. I haven't talked about how, like, behind the scenes we're creating these confusions. And so the way that Sprout does this is it runs the main task with workers. It takes the items that have high disagreement and then passes those to another set of workers, which I'm going to call meta workers, who then diagnose these disagreements. So when they diagnose a disagreement, they either have to clarify the task, or they say, actually, this shouldn't have been confusing, and let's create a test question out of this item. And so the way that they clarify the task is with this task, where they're asked to create a new bullet that would resolve the ambiguity. So here, for this railroad car, the system, they could fill in is a railroad car, and this auto-completes to help with clustering. And then they could say that the answer should be no. We actually throw away these answers, but we just found that it was more intuitive for workers to say what the answer should be. So, because ultimately the requester has to decide, right? But the purpose of this is to do clustering. And so we did a requester user study to evaluate how well this works. We gave them some prompts that were underspecified initially and a data set from previous work, and took 2 domains from previous work, which were these car images as well as a longer travel website task. And the baseline that we compared to is this previous tool for basically solo clustering your data set and determining the instructions. So this tool lets you categorize items as yes or no, or defer the decisions for later in the maybe category, and also create groups to help you keep track of things. You can drag things around. So we recruited some requesters of varying amounts of experience to use these 2 tools. And we found that overall that requesters preferred Sprout, the support that our tool provided. And they said things like categorizing the inputs, showing me the cases where there was confusion, et cetera, made it super easy to identify the cases that needed clarification. And another requester who is an NLP researcher appreciated the similarity metrics, that she found that the suggested test questions were actually performing well. And this was also borne out in the data that people tended to use the suggestions quite frequently. And we did an evaluation of the comprehensiveness of the instructions. We found that requesters tended to write longer instructions and cite more examples, and also that they resolved more of these ambiguous categories using our tool than not using it. But still, we found that some requesters found value to both tools. Like the solo labeling tool didn't introduce any bias. For example, and another one appreciated just doing the task by themselves and like getting to the details. But the trade-off is that someone said it sucks that you have to start from a completely blank slate, and our tool provided more support. So I guess that's kind of summarizes the trade-offs. And there's some previous work, as I mentioned, citing the difficulties people have with task design and the risk to workers, as well as some other requester tools. But ours was the first that both supports exploring your data set as well as editing the instructions. And we found that doing these two in parallel is important. So yeah, to summarize the 3 projects I talked about, I first talked about how we can prioritize work and overcome a combinatorial optimization problem, create efficiency improvements of 10x, theoretical guarantees of batches, and we achieved this using submodular optimization. And then given that the next problem that I talked about was how do we ensure that the workers working on that prioritized work are performing well and have higher accuracy, and do this in a setting where there's a small amount of data. And so our method outperformed the recommended policy by a large amount and was able to handle unobservable rewards. And we did this by modeling the problem as a partially observable Markov decision process. And then the last problem of how do we align the agent's behavior with what we actually want. And we built a tool, a crowd-powered tool for doing this. So in the last part of the talk, I wanted to, I don't have time to talk about all of my current work, but I'd like to give some ideas about future work that I think is exciting in this area. So to give some context for why I think it's important to move to in-task support and more complex tasks, we're facing a job loss crisis with accelerating job loss largely due to automation. And so in the US, for example, and just in the transportation category, there's 1.7 million US trucking jobs at risk. And so where do these people go for work when they lose their jobs? Well, I hope that online task work could provide one place that they could go. But I don't think we want everyone labeling cars. Previous researchers asked the related question, can we foresee a future crowd workplace in which we would want our children to participate? So I think this is a good question and a deep one, but I think one way to get at this is to move from labeling tasks to more complex and creative tasks like writing tasks or design tasks, et cetera. And you might wonder if, do we need to build agents that can actually perform these complex tasks to support workers doing the task? Well, I think the answer is that we don't always need to do this. So suppose your workers are working on a summarization task, like summarizing an article or something like this. An agent can provide high-level guidance in the form of a checklist or a rubric. So the agent could ask the worker, did you check your spelling and grammar? Did you start with topic sentences, et cetera, without actually knowing how to do the underlying task itself. And we have some preliminary evidence suggesting that the requester doesn't need to define all of these, that these can be crowdsourced as well, using workers who can kind of identify attributes of good solutions. But we do have impressive advances in deep learning and deep reinforcement learning. That means that I think agents can start to act inside of complex sequential tasks. So suppose you've trained some AI models, these red guys here, to do some task like question answering. So given a text and a question, what should the answer to the question be? And you might be interested in hiring workers to identify adversarial examples that the models get wrong. And maybe you're interested in doing this for an AI safety reason, like before you launch these models, you want to make sure you've identified the failures that they have. And so this is often called a beat the machine workflow. And the way that it might work is that a worker will guess an adversarial example, edit their guess some number of times until they find an example that the agent actually gets wrong, which is indicated by the green check mark here. And so if we have many workers doing this sequential process, maybe we can start to automate some parts of this, like learn the transformations that workers are applying to the edits that they're applying, and start to have an agent collaborate with the people and perform some parts of this. And I think there's, so you could do this in a couple ways. One way might be like imitation learning, basically trying to copy what the workers are doing. But then this task also has a reward signal, like you can identify which edits led to good solutions, and so you can start to use reinforcement learning as well. And so I think this approach would have multiple wins, right? We would be able to debug the models at lower cost because we would start to train agents to participate. I think the agents that are collaborating would also be like really interesting contributions themselves, as well as creating challenge data sets at low cost, because the adversarial examples that they're finding are probably more difficult. They've already beaten your best models, and so you could release the data sets and for future researchers, for example. And so overall, I see a lot of potential for human workflows to advance AI in science. So I think a good approach to solving a lot of hard problems is to start with a human workflow for them, and then automate parts of that workflow. So for example, AI2 might be interested in creating a workflow to review new archive papers, maybe because you want Semantic Scholar to recommend the best archive papers and not just ones that match your interests, and initially doesn't know the quality of the new papers. So how might a workflow like this work? Maybe you would start to identify the contributions in the paper, link evidence in the paper that supports the contributions, identify limitations, either specified by the author or not, and then use all this information to rate the quality along some dimensions. And again, if you have many people doing these steps, it starts to create really interesting data, which you can use to train AI systems to automate parts of this. Like maybe you can train a system to identify the contributions, to extract contributions or limitations from a paper, or given a contribution to link evidence, or given information to predict a rating that a worker might provide. And so I think this would, like, each of these might be an interesting new AI task that one could release the data set as well as the trained AI agent. So I think this approach is an exciting one, and but it still might be a little bit expensive initially, right? Because you're hiring people to do tasks. So I think another worthy goal is to try to align the work that people are doing with work that they actually want to do. And so one way to do this might be to align these tasks with human learning tasks. That, like, maybe someone wants to learn about a research area, they could answer questions and do work in that area to get up to speed in it. Also personalization, maybe people will be interested in providing work to help the AI agent learn something better about themselves, so the agent could make better recommendations, sort of the Netflix model. Gamification, I noticed AI2 has a new game called Iconery, which is like also another interesting motivation, as well as I think citizen science, since AI2 is a nonprofit, and I think people would be interested in just volunteering their time to do tasks for AI2. And I think people have labeled huge amounts of data in other, like, science domains, and so I think this would be an exciting way to get people to participate as well. So with that, I'd like to just thank my collaborators, my amazing PhD advisors, Dan Weld and Mossam, as well as my postdoc mentor, Emma Brunskill, many collaborators who've made this work possible, and funding sources. And then thanks for listening. So I'd love to take any questions you have.